We are glad to present you, GECO, Geometrically Consistent Embedding with Lightspeed Inference. In this work, we propose a novel method for visual features learning, as well as an evaluation protocol that focus on geometrical challenges like symmetry. In recent years, wide attention has been devoted to foundation models like Dino V2. These models have seen billions of images, and their features show a terrific understanding of objects in the wild. However, recent studies suggest they lack a proper geometrical understanding and they do not natively incorporate a 3D representation of the world. Follow-up sophistications, such as viewpoint alignment or stable diffusion features, improve geometrical awareness at the cost of a dramatic slowdown, which might result in taking seconds to process just a single image pair. The impact of these limitations becomes evident in downstream applications such as correspondence estimation. In this task, given a source image S and a set of query points, the goal is to identify the corresponding key points in a target image. When objects undergo non-rigid transformations, like varying cat poses, partial occlusions and disocclusions can cause ambiguities in the learned features. In the example, the red ear and some pawns are misassigned to their symmetrical counterparts. To address these limitations, we propose a new optimal transport-based learning approach that improves feature quality, and so PCK scores in image matching tasks. Our method maintains fast inference, comparable to the original Dino V2 models. However, we identify PCK's limitations in measuring geometry-based performance and propose a more detailed analysis of this metric, along with a new evaluation protocol. Let's start with our training strategy. Given two images, we consider their local image patches. We pass them through a frozen Dino V2 feature extractor and a trainable low-RA module. This last module is the only trainable part of the method. From these features, we compute the cosine similarity between the patches, obtaining a large and dense matrix. For illustration purposes, we will restrict the discussion to just a few patches. We consider this as a scoring matrix for an optimal transport problem. We use 10 iterations of the differentiable synkern algorithm to obtain a final assignment between all image patches. This also provides the assignments for the sparsely annotated keypoint pairs. Our soft assignment training relies on the three losses. One for the points correctly predicted, the positive pairs. One for points that have been confused with others, the negative pairs, in this example, due to left-right symmetry. Finally, one for key points not visible in one of the two images. As we can see in the feature transfer task, our loss function improves feature localization, resulting in more concentrated feature similarity compared to Geo. Moreover, in cases with a symmetric counterpart and occluded ground truth, our method accurately distinguishes and assigns the key point to the bin. Additionally, our approach is significantly more efficient, requiring 100 times fewer resources than the Geo baseline while being both faster and more compact. Our method shows better performance in 2 out of 3 datasets. Moreover, our model remains close to Dino V2 in generalization on Cub, while Geo shows a significant performance drop. But what about challenges like occlusions and symmetries? Well, PCK is not informative in this regard. PCK measures the percentage of correct predictions, and so it is a black box. It measures performance without discriminating between semantic and geometric knowledge. We propose to break PCK into 3 parts: keypoint pairs, where either the geometric counterpart is not visible in the target, or they don't have a counterpart to be confused with, and those that have a symmetric counterpart visible in the target. During our study, we also noticed that PCK's nature may hide ambiguous predictions. Consider this example: the ground truth position of the left leg and its geometric counterpart, the right leg, appear quite close. Then, should we consider this prediction correct? We discriminate 3 cases. When the prediction is close to the correct position but far from the symmetric mate, we can consider it as a clearly correct prediction. Similarly, when the prediction falls near the wrong one but far from the right position, this is a clear mislabel. However, when the prediction falls in between, The outcome should be regarded as ambiguous. N11 metric, and so PCK, counts ambiguous cases favorably, while the clearly wrong prediction is not quantified. Looking at the APK results, our method's better performance is mainly motivated by much more clearly correct predictions. Notice also that we have less clearly wrong predictions, while ambiguous cases remain stable. This indicates that the features learned by our method are more geometric aware. Finally, we also qualitatively verify our feature embedding on a dense segmentation task. Our features show robustness, continuity, and capacity to correctly characterize the different parts of articulated objects over all their surface. In conclusion, we propose a novel visual feature learning method based on optimal transport and soft assignment. We achieve the state-of-the-art on multiple datasets while being 100 times faster and smaller than the competitors. We develop a deep analysis, highlighting how PCK, while useful, might hide geometrical understanding, and we propose alternative solutions. We will release our code and implementation, which we believe will be useful to foster analysis for geometric awareness in visual feature learning and all related downstream tasks. Thank you for watching.